Hola, muy buenas tardes. Muchas gracias a todos por venir. Queríamos saludar primero al director del instituto, doctor Pablo Raceto, quien en conjunto con todos los investigadores del FONDECYT número 11-20598, hemos tratado de avanzar en la temática de la sociología analítica, la simulación, y en este marco, en el marco de este proyecto, hemos invitado y contamos con la presencia hoy del doctor Gianluca Manzo. El doctor Gianluca Manzo es doctor en Ciencias Sociales por la Universidad de la Sorbona, doctor en Epistemología y Metodología de las Ciencias Sociales por la Universidad de Trento y actualmente se desempeña como investigador en del GEMAS, el Grupo de Estudios para Métodos para el Análisis Sociológico del Centro Nacional de Investigación Científica en Francia. Además, realiza labores de docencia en la Universidad de la Sorbona. Los tópicos fundamentales a los cuales el doctor Manzo se ha dedicado es fundamentalmente desde la perspectiva analítica a los modelos basados en agente y la simulación. Y esta tarde va a presentar la charla titulada en inglés Agent-Based Modeling and Types of Causality, Insight from a Sociological Example. Invitamos al doctor Manzo a dictar su charla y le agradecemos su presencia.
Okay. Thank you. Thank you very much, Christian, for this perhaps too kind introduction. And thank you very much for having me today and for inviting me to Chile. It's the first time that I come to this country, so I'm extremely excited and very happy to be here. I'm learning lots of things, plenty of things about this country, so I'm really excited to be here, so thank you for making this possible, my visiting possible. The topic of my talk today or tonight is the possible connection that we can establish between a specific kind of simulations, namely agent-based modeling, and causality. I will try to address the question of the extent to which we can use agent-based modeling to establish causal relationship. This is an extremely controversial topic. Of course, many of my colleagues involved in the standard quantitative approach to social phenomena would disagree about the fact that we can use an ABM to establish causal connection. My view is a little bit different, so I will try to argue basically three different but related things. First, I will try to convince you that agent-based modeling allows us to implement a generative understanding of causation. Then I will try to convince you that ABM allows us to implement a manipulationist understanding of causation. And finally, I will try to speculate a little bit about the conditions under which ABM allows us to extrapolate to real causal connections. I will try to illustrate these three arguments on the basis of a specific model, on the basis of a specific ABM, which is an ABM of educational choices. But I must say that for this talk, I will not go into the details of the model. I will not go into the details of the theoretical rationale behind the model. This will be the topic of a talk that I will give tomorrow, I think tomorrow morning. So tonight I will use the main ideas and the main results of this model to illustrate these three meta-theoretical arguments, if you want. This is the structure of the talk that I imagined for you. So the first part is the theoretical part. I will introduce 3 different understandings of causality and causation. Then I will introduce the concept of ABM, which is certainly something you are familiar to hear. So perhaps part of what I'm going to say about ABM is trivial for you. So if this is the case, please tell me. I will go very quickly on point 2. And then in the second part, I will try to illustrate what I have said during the first part, and basically I will present the content and the result of a specific ABM. I will try to tell you how we can use this result to argue that an ABM is able to establish or produce causal knowledge. And I will conclude, if we have time, with some notes on the concept of external validity and on what sense an ABM, in what sense an ABM can be used or can be externally valid. Let me start with 3 different understandings of causation. And the 3 different understandings of causation that I would like to introduce are being labeled by the British sociologist John Goldthorpe. Causation has robust dependence, causation as consequential manipulation, and causation as generative process. And as you can guess, the argument is that ABM is related to the second and the third understanding of causation, but not really to the first understanding of causation. In any case, this is the claim that I will make during the talk. Causation has robust dependence. You are familiar with this, I'm sure. So the idea is that we can establish a connection, a causal connection between a set of xi predictors and a given dependent variable if we control for the potential confounders of the effect of xi. In my case, according to this understanding of causation, we can establish, we can claim that the effect of the education of I's father on I's education is a net effect, is a causal effect, if we can control for a certain number of variables that also intervene on yi. So this is the basic understanding of causation which underlies part or a large part of statistical methods or descriptive methods for observational data. A second conception, second understanding of causality is more related or deeply related with lab experiment or natural experiment. And the idea is extremely simple. We can claim that the relation between xi and yi is a causal connection as long as we prove that if we manipulate xi, we produce some effect on yi. So consequential manipulation, because the manipulation of a variable is consequential for the state of another variable. And of course, the main problem within this framework is to find the best or the most appropriate manipulation, right? For instance, in my case, we can imagine some design like in sibling studies in which 2 brothers, one of the 2 brothers is assigned to a family different from his original family with a different socioeconomic background from his original family, and we can study if this manipulation of the background context has an effect on the educational achievement of the two brothers. Okay? Of course, this is difficult to realize, but in the case of sibling studies, this is precisely what we do. What are the problems, if any, with these two understandings of causation? This is the way an important social statistician, again a British scholar, put the limitations of the two previous understandings of causation. Sir Cox wrote, the limitation concern the absence of an explicit notion of an underlying process or understanding at an observational level that is deeper than that involved in the data under immediate analysis. So there is no change in the level at which we imagine some process or mechanism that trigger the connection that we established or observed at the level X. And Sir Cox continues by saying this seems to be an important part of the general scientific notion of causality. So a social statistician, one of the most important of the last century, says this idea of generation is an important part of the general scientific understanding of causality. It's important to stress that it's a statistician that says that, not Gianluca Manzo, not a sociologist. It's someone who created, invented one of the most important methods in social statistics, Cox regression model. So a social statistician tells us statistics is not about causation. Causation is about theory that you have to invent, to create at a deeper level than observational data. And Cox continued, ends the comment by saying, my preference is to restrict the term to situation where some explanation in terms of a not totally hypothetical underlying process or mechanism is available. So this is not some analytical sociologists that want to gain social visibility in the academic world. This is Sir Cox, who proposes a different alternative understanding of causality. And this is basically the graphical representation of this understanding of causality. If you want to claim that xi has a causal effect on yi, you have to provide first theoretical and then empirically some evidence of some underlying mechanism. And this was theorized at the beginning of the 70s from some philosophers of social sciences that perhaps today are considered a little bit old-fashioned, but in any case, the initiator of the critical realism perspective in philosophy of social science called this understanding of causality generative theory of causality compared to the successionist theory of causality, which would be the theory related to the causality as robust dependence. Causality is related to the sequence of events if you, of course, can prove that this sequence is not spurious. What I would like to argue is that these two understandings of causation, causation as manipulation, consequential manipulation, and causation as generative process are especially can be especially well combined with ABM. Okay? So let me introduce the second part of the statement, ABM. What's an ABM? An ABM basically is a computer program. And this is the nice definition from the British computer scientist Wooldridge. A multi-agent system is one that consists of a number of agents which interact with one another, typically by exchanging message through some computer network infrastructure. And an agent is a computer system, more or less complex, that is capable of independent action on behalf of its user or owner or programmer. Okay? More pedagogically, if you want, or more visually, an ABM is a set of individual and relational entities. By relational, I mean basically links. It's a set of attributes that we assign our entities. It's a set of tasks or rules that entities have to perform. It's also a local context which can be relational or spatially, geographically based. Of course, an ABM also contains some boundaries. And then, no simulation without temporal scheduling. So an ABM is also made of a temporal scheduling. And by iterating over time the rules associated to each individual and relational entities, we are able to trigger some high-level patterns that hopefully were not contained in the starting conditions of the simulation. What is important is the link that we can establish between an ABM and the specific type of programming language that we use to write an ABM. Because my idea, my view is that the flexibility of ABM to implement generative and a manipulationist conception of causation derives from the specific language programming that we use to build this kind of device. And this specific language is object-oriented language. What's an object? An object is a computational entity, numerical or symbolic entity, that encapsulates some state, are able to perform actions or methods. Action and methods are the same as tasks and rules. Methods is more related to specific language that use this concept to speak about rules or tasks that we associate to entities. So able to perform actions or methods on this state and communicate, again, interaction, exchange, by message passing. So an object is a set of properties and a set of tasks, and we can make object interact. So this is not completely accurate, what I'm going to tell, but if you want to give up the concept of agent and think in terms of object-based models, you can do that. From a computational point, it's not exactly accurate, this substitution that I'm suggesting, but from a conceptual point of view, we can accept the idea that what matters is that we program, we design object. And of course, there is the meta concept of class, but it's not important in this context. So what's important is this. My claim is that we can use ABM to model mechanisms, which is why we can use ABM to implement a generative understanding of causality. I think that this claim is based on something deep, which is the deep correspondence between the concept of mechanism and the content on an ABM. Let me try to explain this point, which is an important point for me. Let me define a mechanism, a real-world mechanism, as a set of entities, for instance, individuals, but it could be cells or particles or whatever you want to model. So a set of entities, a set of entities properties, a set of entities activities, and entities connection. Let me give this general definition of what a mechanism is. Often these mechanisms are unknown, and even more unknown is the sequence of events that these mechanisms is able to trigger. But what from an explanatory point of view, what matters is precisely this process, because this process is responsible for the real-world high-level patterns that we observe. What we do usually within the standard statistical framework is that we infer the mechanism from its statistical signature at the aggregate level, right? Now let's go to ABM. What an ABM? An ABM, we have just seen, is a set of objects, entities, objects. The set of object attributes, entities, properties, object task, entities, activities, and object communication, entities, connection. So there is a deep correspondence between what we want to model and the way we model it. But there is also a deep, an important difference. While the real-world mechanism is unknown, or very often unknown, the artificial mechanism is completely known. We design the mechanism. And by simulation, we trigger the process associated to the set of artificial mechanisms that we design. Now, I agree that it can be difficult to understand the dynamic of the model, but in principle, this is known or knowledgeable. And by this process, we trigger high-level patterns. So you see, we are in a very different situation. Here, we are obliged to infer the mechanisms from its high-level statistical signature. Here, we generate the high-level patterns from something that is completely known. So this is why I claim that ABM can be used to implement a generative understanding of causation. And this is the correspondence or the application of this scheme to the model that I'm going to present, even though very quickly. In my case, I use object to represent actors. My entities are actors. I use object attributes to represent perception and abilities of actors. I use object task to represent the balance that actors have to find between perceptions of cost and benefit of education and their abilities. And I use object communication to represent social networks. I can simulate this artificial world. I can trigger a sequence of structurally constrained interdependent educational choices, and I generate the pattern of intergenerational educational mobility. Right? Here you have a nice quotation from an important, I think, scholar in this field about this connection I'm trying to argue for about ABM and a generative understanding of causality. Epstein wrote, "Perhaps one day people will interpret the question, can you explain it, as asking, can you grow it? Right? Artificial society modeling allows us to grow social structures in silico, demonstrating that certain set of microspecifications are sufficient to generate the macro phenomenon of interest. I will, in the last part of the talk, I will say that in fact ABM is able to do something more than just figure out conditions that are sufficient to generate macro phenomena. So here you have a clear statement about the connection between generative understanding of causality and the technique. And here you have an even more general statement that I have found very recently, but I think it's a fantastic statement by the expert in logics, Gregory Chatin, who said, well, the computer changed epistemology, changed the meaning of to understand, but if you substitute causality to explain for understand the bulk of the quotation doesn't change, to me, you causally explain something only if you can program it. This is an extremely deep idea. If you don't program it, if you don't grow it, you cannot claim that you are causally explain something. You can claim that you are causally explain the functioning of a clock if you are able to program the clock. If you are not able to generate the clock behavior, you cannot claim that you understand and you causally explain the clock behavior. This is the idea, deep, in my view, deep idea behind this quotation from Gregory Chatin. Otherwise, you don't really causally explain, you only think you understand it, right? Okay, so now I would like to illustrate these perhaps two general claims on the basis of a specific ABM. But perhaps you have some questions before or criticism or, yeah.
What about, you know Gödel's theorem, like there are certain tasks that are not decidable by a computer.
Right.
And these are only mathematical tasks, not even emotional tasks or going to this like more complicated I don't know, domains that don't have even a mathematical representation, so they cannot even be programmed so far. So yeah. What will you do with the understanding of something that is undecidable, like
it's a fantastic question.
Generative grammars?
Yeah, thank you. My answer is that let's imagine that you create a model in which actors have to maximize something. And let's imagine that you are not able to solve this problem. So we are in a case, at least from a logical point of view, comparable to the situation, the scenario that you described, or Gödel described. This is a fantastic result, because if computationally, analytically, and computationally, you are not able to solve a problem of maximization, how could you claim, for instance, that this model is interesting or helpful to represent a real problem, right? And can you imagine that, I mean, in economic theory, we have had 50 years of models that basically are not computationally solvable over a scale which is relevant for real actors. Of course, if you think in infinite terms, you can perhaps solve the model. But if you think over a scale of 10 years or the scale of a life of a real actor, we, not most of the time, but very often relied on models that are analytically and computationally unsolvable. So the conclusion that I would draw from the fact that a given model is not solvable from a computational point of view is that if the computer is not able to solve this, I cannot claim that the model is something relevant for the reality. Okay, this would be my answer. Not relevant for the reality. Okay. If the computer is not able to, you find the discussion of this argument in the second chapter, not of this book, but the more recent book by Epstein. What's the title of the book? Generative Social Sciences or something like that. In the second chapter, you have a deep discussion of the implications that you should draw from a model which is not analytical and computational solvable. And basically the argument of Epstein is the argument that I have just proposed as an answer to your question.
Yeah, it's pretty radical.
It's pretty radical, yes, but if you want to convince me that this is not the right answer, you have, the burden of the proof is on you. You have to prove that if the computer is not able to solve a maximization problem, the frame that you use to model the real problem is relevant for real actor. If the computer is not able to solve the system of equations that you use to model them, how they can be able to solve the problem. So if you're not convinced by the answer, you have to answer this question. Well, you can continue. Discussion is a fantastic discussion, of course, and very deep. Anything else?
Yeah, I think very different programs in principle can generate or produce the same high-level patterns.
Yeah.
So the mere fact
I will
that
reply to this question at the end of the talk.
Okay.
I guess that the question is, how could you trust this? Yeah, I will reply. I will reply at the end of the talk. Yes, so let me try to illustrate the three arguments on the basis of a specific ABM. And the ABM is an ABM of educational choices. I know I have just learned that here you are deeply interested in school choices. This is a model of educational choices. So what I want to explain at the micro level is whether or not an actor is disposed to enroll in a given educational level. So it's a choice about I continue or I stop. And the mechanisms are about the choice of continue or stop. It's not a model about what kind of school I would like to go to, given that I have chosen to continue to that educational level, right? So the problem is educational choice and not school choices. So we'll see in a minute the content of the mechanism that I put behind the actors or agent choices, but let me start with the high-level patterns that I would like to generate. This is the real-world patterns, as long as you believe that survey data provide you with real-world patterns, but this is another question. So I assume that survey data are able to provide real-world aggregate patterns. And here you simply have, this is a visual representation of a cross-tabulation. Cross-tabulation of what? Of the respondent highest educational level attained by the highest educational level attained in the past generation, right? So this blue square should be read more than 40% of French men and women coming from parents with no elementary complete education also fall in this undesirable educational destination, right? This is the so-called Casmin educational classification. Blue is elementary, completed or uncompleted elementary education. This is general or vocational completed elementary education, lower secondary education, upper secondary education, and tertiary education, short and long tertiary education. But I would say that the specific classification that we use doesn't really matter for my purpose. Okay, so we can see lots of facts, lots of empirical facts in these patterns, but for the goal of this talk, let's just concentrate it on what we can call the polarization of educational opportunities. Here, what I'm reporting on here is the generalized odds ratio for people from the no-education background to reach the no-education background. So it's a measure that tells us what's the probability, even though technically it's not exactly probability because there is no modeling behind this, but it's the probability to get these destination rather than any of the 4 other destinations compared to all other educational backgrounds. It's the generalized probability to get this educational outcome rather than any of the other educational outcomes. And you see that this is extremely high, so there is a sort of educational trap for people with no education background. And at the other extreme of the educational ladder, there is a favorable, in a way, educational trap for people who come from the tertiary educational background. They have a very strong chance to also end up with a tertiary educational level, right? So we have a sort of polarization of educational opportunities. People who comes from a very deprived educational background tend to remain within this educational background, and at the opposite of educational level, people who comes from a rich educational background tend to end up with a rich educational background. This is France in 2003, right? So this is the country of educational opportunity, right? Okay, so this is the macro structure that I would like to, this is real data, right? This survey data. I aggregate information and I get these micro level patterns of intergenerational educational mobility. Now my problem is I want to generate this pattern. So I want to establish a connection between a low level set of rules and these patterns. So which would be the proof that I'm able to establish a causal connection between the low level and the high level, right? What's the model about? So I designed an ABM which is composed of 5 groups of agents, and even though at a smaller scale compared to the empirical data that I have just shown you, the size of each group of agent reproduces the size of real groups of agent in the sample that I want to reproduce. And I obliged my agent to make 4 sequential educational choice, so they have choose if they want to enroll to the educational level which is labeled 1 in the model. If they decide to enroll in this first educational level, then they can consider the second educational level. They have to make the decision if they decide, and so on, right? So it's a model of sequential and conditional educational choice. You cannot choose to go to tertiary education if you don't complete the elementary education, right? So it's exactly the same framework as the standard statistical framework based on binary or multinomial logistic regression from the side of on the side of empirical, quantitative-oriented sociologists. Of course, by simulation, I'm able to let this system evolve a certain number of iterations, and hopefully, I'm able to produce something comparable to the cross-tabulation that I have just shown you. There is no empirical data in this model. There is anything related to the cross-tabulation that I want to produce, except the size of the group of agents which are supposed to represent real-world groups of actors, right? So basically the smallest group of agents represent the agent with parents from the highest educational background, and then the most numerous agents are those from the lowest educational background, which is a quite usual structures in real societies, no matter if you consider educational background or socioeconomic background. So as you can see, agents are embedded in a network of links. You can see that there are some links among agents belonging to the same educational group, and links that related agents from different social groups. The networks is basically a small word network which is built on the basis of a modification of the standard beta Strogatz-Watts algorithm, and the modification concerns the fact that I have links among agents belonging to the same groups, but I also have links to agents belonging to different groups, and in order to represent the idea that social networks are tendentially homophilic, to create the intergroup link, I have a set of parameters that basically says that the larger the distance between two agents in terms of the educational background they come from, the lower the probability that an intergroup link is created, right? So basically, I'm designing a model in which, as I said on the right side of the slide, most of the ties are in-group ties, so people tend to be related within their own educational group or educational background. If you have son of a lawyers, you tend to have friends that are lawyers, son of lawyers too. Most of the out-group ties, the weak ties, if you want, if you like the Granovetter's terminology, most of the out-group ties connect agents belonging to groups that are socially close. And of course, the part of the analysis that I use to prove the statement about manipulation causality will be about to manipulate these network structures, right? But now I will show you what the model produces when we adopt what seems a realistic network structures, basically a network in which homophily dominates, right? Okay, so this is the relational context in which agents are asked to behave. Now, let's look very quickly at what each agent has to do. So the way, this is the real model, I mean, the way I model educational choices. The educational choices is conceived as a probabilistic decision, which depends, this is a standard logistic function, which depends on the strength of the preference of the agent for the educational level he is considering. And this preference depends on agent ability, agent perception of benefits of the educational level he is considering, and this is, I would say, the original part of the model, on the educational choices made by the agent's neighbors. And here you have the way I model the social influence term, this fractional social influence term simply tells you that the larger the number of neighbors that decide to enroll in the educational level L, the larger the probability that the agent follow, the agent also enroll in this educational level, right? So I'm representing here a sort of educational conformism, of course, according to the composition of the agent neighborhood. This term would trigger more or less educational conformisms given the educational background of the agent, right? If I have an agent from an educational background which is surrounded by high-level agents who perform very ambitious educational choices, this term will tend to push my low-level agent toward positive educational choices at the highest level of the system, right? So it depends, of course. If here I have something like the networks they have designed in which homophily dominates, this term should trigger deep educational conformisms, thus deep educational reproduction, right? Okay, so there are lots of technical details involved in this. Let me just say that ability, agent abilities, and agent perception of benefit of the educational level the agent is considering don't come from empirical data, come from probability distribution. So I'm just playing with numbers, right? And you can object, how could you argue that the distribution of ability and cost benefit perception across social group is a realistic distribution? If you ask the question, I will give you the answer. So keep in mind that numbers for the ability mechanism and the benefit mechanism comes from exogenous probability distributions, namely log normal distributions. What I'm going to show you is what happens when we simulated the model by introducing only ability, then we add benefit perceptions, and then we add the homophilic social network component, right? So I first simulate my artificial world on the basis of agents that only look at their, let's say, grades, for instance, their cognitive ability. Then I let the system evolve by adding benefit perception, and then I add the social network component. And each time I assess the proximity between the simulated educational stratification and the empirical educational stratification. Okay, so the simulated high-level patterns. Here you have the result generated by the model when only agent ability matters. So the second and the third mechanisms are absent from the artificial world, right? And you can see that basically we don't have lots of social differentiation in the educational, distribution of educational certificate. Here, let's focus on the highest educational level. At the highest educational level, this is French data. This is the real distribution. I have just isolated one of the columns of my cross-tabulation. And this is the column that you can look at if you want to compare model and simulated data. So you see that the distribution is extremely different, which is reflected by the difference that exists between the real world generalized odds ratio for this educational level and the generalized odds ratio computed on the simulated data. The model, under this assumption that only differentiation in agent ability matters, is not able to generate the large amount of educational inequality that we observe in real data. Odds ratio close to 1 means equality of educational opportunity. Right, so the model under this assumption is basically not able to create the amount of inequality at the highest level for the highest, for the agent from the highest educational background. Now let's see what happens if we introduce also differentiation in agent ability, agent perception of benefits of education. You see that the distribution, some form of differentiation across group emerge. You can say that the distribution gets closer to the structure of the empirical distribution, and you see in fact that the amount of educational inequality generated for this group at the highest educational level is also increasing, right? Here we were around 1, so basically no educational opportunity. Here we are around around 3, which is a quite high level of educational opportunity given the measure that I'm using here. But still quite different from the measure computed on the real data. So basically differentiation in agent ability and perception of benefit of education is not enough to generate the real world educational stratification. Let's introduce the social network part of the model in which agents tend to basically reinforce each other at each educational level, right? And this is what you observe. Fortunately for me, for my chance of publication, now you can see that the simulated distribution matches extremely well the empirical distribution. And you can see that the amount of educational inequality for this group at this educational level is quite close to the real world level of educational inequality, right? So I generated a macro level structure which is quite close to the real world structures. But you can see if you look at the general picture, you can see that the general picture is very close to the cross-tabulation that I visualized at the beginning of the second part of the talk. So the moral of the story here is that if we look at something that assess the general fitting of observed and simulated data. This is basically the dissimilarity index computed on the observed and the simulated cross-tabulation. You see that compared to a model in which agents basically choose randomly, when we introduce the differentiation of ability, we increase the fitting of about 17 percentage point. When we introduce the differentiation of benefit, we get 9 percentage point more. And when we introduce the social network component of the model, we get 5 percentage point more in terms of fitting, and we reach a general, an overfitting of the educational, the observed educational stratification compared to the simulated one, which is quite good. I mean, the dissimilarity index around 10 for from something that doesn't contain any empirical data and any empirical information is not that bad. Okay? So the moral is you need differentiation in terms of ability and benefit, but if you don't have some reinforcing mechanism going on, you are not able to generate this sort of educational traps that we observe at the extreme of the educational stratification. So this is not for the talk of today, but I'm not claiming, like some people involved in this kind of literature that networks matter and only networks matters. No, I'm claiming that networks are necessary to complement what social differentiation in terms of ability and benefit produce. Without network, we are not able to get close to the empirical stratification. But I think that I have, compared to my first argument, I think that I have shown you that my ABM is causally generative. At the beginning of the process, I didn't have anything related to my educational stratification. I generate this from bottom up. So I think that this is an illustration of the argument that an ABM can be used to implement a generative understanding of causation. Let me go to the second argument about manipulation. So the second argument, you remember, was that an ABM is also a helpful device to implement the understanding of causation as consequential manipulation. So the idea that you can claim that a connection is causal if you are able to show that if you manipulate X, you observe some effect in Y. Of course, then we have the problem of under what level the manipulation is consequential. I mean, what's the size of the fact that we can consider as an indicator of the fact that the manipulation is consequential. But this is another problem. So now let me illustrate how I used my model to implement this idea of causation as consequential manipulation. A first group of manipulation consisted of, I took exactly the model, the variant of the model that generated this structure, which is the structure that the most matches the empirical one. And then to show that the net effect of the network component, I take exactly the same model with exactly the same initial distribution, with exactly the same seeds. Everything is comparable, but I turn off the network component. This is a quite radical manipulation. We cannot do that in the real world. I claim that we cannot do that within the statistical frameworks. We can do that within the ABM. And this is the result. These are French data. This is the distribution of educational outcomes at the highest educational level without the social influence term, and with the social influence term. It's exactly the simulation that I have shown in the last slide. Exactly the same. I turn off the social influence term and I turn on the social influence term, and you see that this distribution of educational outcomes is much closer to this one than to this one, right? The skewness of the distribution can be produced when the social network part of the model is present, but cannot really be observed, cannot be produced to the same extent as the empirical one when the social network part is absent from the model. So this is a radical manipulation. I manipulate something, I simply let a mechanism be silent, and I observe the effect, and the effect is quite consequential. Here, you have a different parameter manipulation. In this case, I cancel out a piece of the model, the very radical manipulation. Here, I'm just changing the values of a given parameter which is related to a given mechanism in the model, and in particular, I'm modifying the network degree. So I'm allowing agent to be more and more surrounded by other agents. So the connectivity, the average connectivity of the networks increase when you move to the right side of the graph, and decrease when you move to the left side of the graph. This is the value of the parameter on average 4 neighbors that I use to generate the empirical structure, and I can argue why I use this specific value, but this is not relevant for this talk. But there are good empirical and theoretical reasons to think that for this kind of problem, low connected networks are the more realistic networks to use. Okay, so what you see in this graph is basically that what matters is moving from no network to some neighbors, but then when we increase the number of agents that each agent has as a neighbors, basically doesn't produce any effect at the aggregate level in terms of differentiation of the educational outcomes. So in this case, I would say that the manipulation is not consequential. It's not consequential, but this is a negative result that can be used to say, in my model, what matters to explain the dynamics and the outcomes of the model is not network degree, is something else. So you remember the quotation from Epstein, sufficient condition. This is something more than sufficient condition. The sufficient condition was I need networks to generate the amount of. But I can also eliminate some aspect of the model that don't seem to produce effect. So the model is able to give us knowledge about the sufficient conditions, but also to eliminate some aspect, right? Okay, so if network degree doesn't matter, perhaps what matters more is the amount of heterophily or homophily of the network, which is in a way what we would like to prove. If you are surrounded by similar agents, you tend to reproduce the most frequent choice within your social group. If you are connected with agents outside your group, you should be able to generate more educational inequalities. It's the strength of weak ties, if you go back to the classical hypothesis in our discipline. And this is what happens if you increase the proportion of out links, so the proportion of links that link agents from different educational background. Here we are in a world in which agents are more and more connected outside their group until the extreme scenario in which agents are only connected outside their group. Here we are agents that are completely connected within their group, right? So here I'm destroying the intergroup part of the network, okay? So this is the most homophilic word, and this is the most heterophilic word. But please keep in mind that the structure of the intergroup link is still the structure according to which the larger the distance between two groups, the lower the probability to be related. So here I'm certainly connecting all low educational background agents outside the group, but they are not all connected with the highest educational background, right? They are all connected with the two groups that are close to them, but they are outside, connected outside, completely outside their group. So what you see, basically, is that compared to a world which is completely homophilic, the amount of differentiation across group decreases. So that's a proof by parameter manipulation that the social composition of the agent neighbors really, I mean, within the model is able to reduce the amount of social differentiation in the educational outcomes. And here you have the generalized odds ratio computed for each values of the parameter that concern the proportion of outgroup links. And you see that because these graphs is concern only agent at the highest educational level. Here you have an assessment of the general amount of educational inequality within the simulated cross-tabulation, and you see that there is a generalized decrease in the association between the educational origin of the agent and the educational destination of the agent, right? So really, weak ties tend to generate more educational inequalities at the aggregate level. Okay, so I think that I have shown you that an ABM can be used powerfully to implement this idea that causation is or can be conceived as consequential manipulation. In one case, I turned off a part of the model and I generate some consequences that are, and I show that these consequences are different from the case in which the mechanism is present. And in the second case, I changed the value of some crucial parameter of the model, and I showed under which condition this manipulation is consequential at the aggregate level. Now, the third argument is about, but does this model really tell us something about reality. And this is the difficult question. So the third argument was, under certain conditions, we can claim that the causal connection established within the artificial world can be extrapolated to the real world connection. So what are these conditions? And this is related to me, at least partly related to what one can call robustness checks. So what I have used as an illustration of my general arguments is a model of educational choices presented in these papers. You have the complete reference in the last slide. But in fact, I worked on this model. I have been working on this model for a certain number of years. This was my first, at least in France, important publication on this topic. And in fact, the model that I presented very quickly today is quite different from the model that I presented in this book. So let's say quite different compared to the first variant of the model. What I changed? I increased the number of groups of agents that I represented within the artificial world. I presented today a model in which educational choices are modeled as probabilistic choices, whereas the first version of the model was a deterministic choice model. I reduce quite dramatically the amount of parameters that I use to represent ability and cost and benefit perception. So in the first version of the model, I was in situation which statistically is called overfitting. I had more parameters than the number of cases of microstabulation that I want to reproduce, right? Now I'm in a situation in which the number of manipulable parameters are much lower than what I want to reproduce. I introduced a different representation of ability. I destroyed or simplified a part of the model related to population-mediated interdependence among educational choices. I simplified the agent scheduling. I changed the programming language. The first variant of the model was programmed in Java. The model that I have presented today was programmed in Netlogo. I used different data to test the model. So this is a quite large number of variations. And still, the message is that if you look at the book and if you look at the papers, you will find that even though I stretched my model, I tried to change not almost everything, but almost, the model is still capable to generate realistic educational structures at the micro level. So this is what I consider a series of relevant robustness checks. I try to destroy, in a way, the capacity of my model to generate something, and still it's able to generate what I want to explain. So I think this is an important ingredient of the possibility to extrapolate to real world the knowledge produced within your own model. If, as soon as you change something in your model, you get a different and very different result from what you want to reproduce, probably your model is not as much trustworthy as it should be, right? So the answer to the third argument is, I think that these sequential and constant variations that I implemented prove that the model is robust, so we can trust the model's capacity to generate realistic educational stratification at the aggregate level. So let me, this is just a summary of what I have just said. So let me conclude about a note of external validity. In a word, what I have tried to demonstrate is that you can use an ABM as a causal device, right? You can use an ABM to produce causal knowledge. And in the last part, the third argument is part related to the transition from the world of the model to the real world, right? So to what extent, more generally, we can consider that an ABM, a given ABM, is externally valid? So to what extent can we trust the model as providing useful and deep insights of the real world? This is the argument of a quite well known, at least in this field, but probably more generally, philosopher of social science, which in this very interesting article basically compared lab experiments and simulation in the field of physics of fluids. And the argument of Winsberg is that there is no real difference between lab experiment and simulation, in the sense that both methodologies can claim external validity to the extent to which they, experiments and simulation, are built on principles that can be considered as trustworthy. What's a set of principles which can be trusted according to Winsberg? Principles that are theoretically sounded, principles that are related to physical intuitions that can be considered as sound, and that's very important, soundness of computational tricks that you employ. The techniques that you use and the way you use your techniques is important. I think this is a very good and wise, realistic, perhaps not so wonderful as we would like, but I think it's a realistic representation of the validity problem of simulations. I would like just to complement a little bit this argument by saying that an ABM can claim external validity as long as it's built on realistic and empirically supported microscopic theories. So, the first point is related to your question. Numerically, you can always find 2, 3, 4, n variants of a given model or several models that trigger, and we also have this exchange during our meeting. You can always find several models of different variants of a given model that are able to trigger a similar proximity within the simulated outcomes and the real outcome. What can you use to discriminate across these variants or these models is empirical knowledge. So this is the idea of injecting empirical data within an ABM precisely to exclude, in my case, for instance, probability distributions that are not realistic. So I use log normal distribution. Is it realistic to consider that abilities and cost and benefit perception are log normal distributed? Yes or not? Let's look at data, if we have data for this, and if the empirical distribution follow a given probability distribution, let's use this distribution. And if numerically a given model produces the same result, I don't care about this. I know that in the reality, this is the distribution. I use this distribution in my model. If my model is able to generate realistic patterns, this is, for me, the good model. Okay? So first condition, try to maximize the number of empirical information that used to constrain at the micro and the network level your ABM. Second element, the realism of the simulated microscopic consequences of the model. And this is something that I shown in my presentation. So I had a specific patterns that I wanted to reproduce. If my model is not even able to reproduce these empirical patterns, it's difficult that I claim that the model tells me or us something about the reality. If the model is not even able to reproduce what I want to explain, I can always argue that this is interesting for conceptual exploration and this open our mind, if you want. If you use the model to say something about the reality, I don't think this is an argument, right? If your model is not able to generate what you want to explain, please don't tell me, yes, but still this is interesting. Perhaps, but lots of things are interesting. If you use a model to generate something and the model doesn't generate what you want to generate, please don't try to convince me that the model is interesting, right? So second condition for claiming external validity is realism, not only at the micro network level, but also at the micro level. Robustness checks. If you change some crucial elements of your model and still your model is able to generate what you want to explain, this is an additional condition that you can use to argue that the model is externally valid. And then, in fact, I realized that I commented point 1, but in fact I had in mind point 4. I'm sorry. Point 1 is not about injecting empirical information. It's only about the argument that you can use to prove or to argue that your micro network level assumptions are realistic and empirically based. Point 4 is more demanding, and it's exactly about injecting empirical data at the macro network level. So it's a difference of degree between 1 and 4, but it's an important difference. Okay, so I'm sorry, but still, I mean, the argument is clear. And this is something, for instance, that the model I have just shown you doesn't have. I mean, I don't have data to input crucial elements of my model at the micro level. I don't have data, so my model doesn't go through, doesn't pass this criterion. What should I do? I tell you honestly that my model doesn't go through this step, or didn't go through this step. I think that the model passed the first 3 requirements, not the 4th one, basically because I don't have, for France, data fine-grained enough to inject this data in my model. So at the micro level, I may be wrong. Okay? So I should take precautions to claim that my model is externally valid, even though it is realistic and I can prove, I mean, this is not tomorrow I will spend more time on this. I can prove that the model is based on the best theories and the best empirical knowledge that we have in this field. I have proven the realism of the micro-level consequences. I have proved the robustness of the model. But 4 is not, the fourth requirement is not fulfilled. So at the moment, this model cannot claim completely external validity. I'm sorry about this, and thank you very much for your attention.
Just out of curiosity, did you evaluate in the connectivity of your network if there is any difference when you connect different cluster of different education level with key nodes, with key agents, so agents that are more connected with another clusters? Or this is not about agent model based? I'm not that familiar with this specific type of model. Thank you.
It's just about the point 1 of the last diap.
Yeah?
I'm not pretty sure I follow right about microscopic theories. Yeah, empirically supported microscopic theories. In the in social modeling, what I have in mind is psychological theories. Yeah, I'm not sure if that's the point or not. What are the microscopic theories in this case?
I have a complicated question. If we think in the structure of your argument, you have two parts. One is the competition among three ways to understand causation. That is a philosophical problem in some sense. And you say that agent-based modeling is a way to implement some of them. In some sense, we think that this implementation is an argument supporting this these two ways to understand causation. But in some sense, we can think the contrary thing. I think that if we think particularly in the two previous questions, we can think that agent-based modeling may show that these ways to understand causation are in bad ways. In what sense? A good way to understand the concept of a causation is giving necessary and sufficient conditions to understand causation. But agent-based modeling say, and connected with the previous questions, say, okay, this way to understand causation, particularly in the main generative, is not sufficient. Why? Because we can have many agent-based models that obtain the same results. Then, if you have even a very good agent-based model, you cannot have proofs that you are catching the relations of causation. And the contrary argument is these criteria are not necessary. Why? Not only because Gödel and theorem and these things, but for the idea of emergent properties. Emergent properties have two colors, yes, weak emergency and strong emergency. In the simulational way to understand weak emergence, typical of Bedeau, in which we say something is weakly emergent if we can only obtain the result by simulation. But we have the idea that there is strong emergence, see, like mind or consciousness, in which we cannot a mechanism for the generation of mind, for example, but we know that there is a causative relationship between neurons and mind, even without a mechanism. Then we can say, if we cannot have an agent-based modeling to explain mind, even though I can say, because the other criteria, that there is causation in these cases. Then, in summary, I think that agent-based modeling can be a bad favor to the theory of these two kinds of concepts of causation.
Okay. Let me start with the two first questions that are more are easier than the third one. So with respect to network degree, the algorithm behind the network that I used is an algorithm that fixes network degree. So the heterogeneity of network degree is extremely low. So in this sense, there is no bigger or biggest nodes and nodes without connection. So when I inspected the distribution of degrees, the average is really the average fixed at the beginning of the process of network generation, and then you can have a variation which is really, really low. I mean, let's take the scenario in which the average degree is 4. You can have nodes with 6 or 7 links, no more. So I don't think that it would be meaningful to try to connect agent with stars in a way, because there is no really stars, given the way the algorithm is, given the way the networks is generated, right? Yeah. By the way, I'm not sure that theoretically, for the problem that I'm trying to model, it would make sense to think in terms of stars. Except if you conceive stars as within group stars. If you consider that there is a given group, there is a leader that dictates in a way the right educational choice that the other actors have to follow. Is this realistic? Not sure, but.
Just professors as example.
Pardon?
As example, just professors.
Yeah, but this is outside the model. I mean, I'm modeling interactions among peers, not interaction between actors, between pupils and teachers or whatever else. I have only dyadic interactions that want to represent interactions among peers. Okay? Yeah, okay. I mean, it would be another model to introduce the behavior of another group of agents, like teachers, for instance. But of course, in this case, from a model point of view, it could be modeled as a star mechanism, I mean, an all-to-all communication from teachers to every other agent which is within the class. But to do this, you would need a representation of the educational system, of classes, and so on. I mean, it's another kind of model. If you consider that the only macroscopic theories, only relevant macroscopic theories are theories that go to the cognitive or emotional level, in this model there is not this kind of macroscopic theory. The macroscopic theories behind these model is the so-called rational educational approach, which is based on the idea that for educational choices, what matters are abilities, cost, and benefit perception. This is the Boudon, Gold, Breen models of education. And what I introduced in the model is the idea that you need ability evaluations, cost and benefit evaluations, but you also need the educational behavior surrounding the agent, because the behaviors of others provide the agent with information, with values in a way, and possibly with microeconomics, scale microeconomics. I mean, you can share the apartment, you can share the notes, you can share the cars, this kind of things. So you tend to follow others because you have access to resources that you wouldn't access if you would do a different educational choices, right? So there is no deep, from a cognitive or emotional point of view, deep microscopic theories. With respect to your question, I think I have answered to the first objection, or at least I considered the answer that I have given to the previous question. I don't care about the fact that several micro-level specifications of the same model, or that several models produced numerically the same outcomes, as long as I have empirical information to say that there is one variant of the same model or one model which is more realistic than another one. Okay, so to me, it's not an argument, the fact that in principle, numerically, you can build models that are equivalent in terms of the patterns that they are able to generate. Okay? So if the discrimination, the selection of the right model is an empirical matter. So once you have shown that a given model is sufficient to generate eggs, then you have to prove by theory and on the basis of the available experimental and empirical evidence that the model that generates the outcomes is realistic. And this is, again, an empirical and theoretical problem. So I don't think that the argument that in principle several micro-level instances can produce the same outcome is an argument against the generative capacity of an ABM. It's a problem from a logical point of view, that a logical problem that has an empirical, in principle, solution. As long as you have data, and if you don't have data, you accept uncertainty. But uncertainty is part of our scientific activity. So as long as you don't have, you remain in your doubt about the model. That's academic life, scientific life, and I think, okay? So, but it's not an argument. I don't think it's an argument, right? The second point, personally, I don't believe in the distinction between weak and strong emergence, and I have serious problem with the concept itself of emergence. But this is my personal view, and we can discuss this. But if I accept this distinction between weak and strong emergence, still, you can claim that the evidence that there is a connection between the neural activities and something that we call awareness, the simple evidence of this connection, if you want to label this connection as a causal connection, you can. This is causation as robust dependence. as long as you are able to prove that this connection is robust. But as several authors have proposed, this can be considered a superficial understanding of causation. You have this nice quotation from Chattin, which is, otherwise you don't really understand it. You only think you understand it. This is for me the main point. You can claim that there is a co-occurrence between neuron low-level activities and something called awareness. This is causation. Why not? I think this is superficial from a causal point of view because you don't know the mechanism that generate this connection. And historically, you have plenty of examples in biology and in physics in which knowledge improves when mechanism was discovered. I mean, I think that we can continue to discuss this difference of views for decades. And to me, it's not deep enough to establish a connection and to call this connection causal connection, if, as long as I don't know what are the mechanisms that generate this connection. You can claim that the connection between smoking and certain kind of cancer is a causal connection, is a robust connection. From a statistical point of view, it is. But as long as you don't know the biological mechanisms at the level of cell's life and cell functioning that explain this connection, in my opinion, you are not claiming something which is deeply causal. I mean, on this point, probably it's just a matter of personal satisfaction or dissatisfaction. And this is why you said I presented alternative views of causality. I don't think that I framed my argument as alternative. I claim that if you believe that the causation as robust dependence is not deep enough, and if you want to achieve something called generative causation and causation as consequential manipulation, if you believe in these two understanding causality, you have a tool that's able to represent, implement these forms of causality. This is my claim. I'm not saying that there is a right and a wrong concept of understanding of causality. I think that in terms of knowledge, there is something deeper, which is different from saying that it's wrong. I'm not saying that methods to discover robust patterns in data are wrong. I'm saying that they cannot say a certain number of things. And if we believe that our knowledge improves, if we are able to say a certain number of additional things, we need other methods. This is my claims.
Agradecemos nuevamente la respuesta del doctor Manzo, y para quienes quieran seguir profundizando en estos temas, esta es solamente la primera de las conferencias de Gianluca Manzo en Chile. Agradecemos su presencia, agradecemos nuevamente al doctor Manzo y nos despedimos con un aplauso.
Thank you. Thank you very much.